From Canada's Perimeter Institute for Theoretical Physics, welcome to Perimeter Explorations, classroom videos that investigate the frontiers of science. Join narrator and physicist Damien Pope of Perimeter's outreach team and leading scientists and engineers as they take you on an educational journey of wonder and discovery.
Things are unexpected, surprising.
Einstein once said, the world cannot be that crazy. But today, we know it is that crazy.
The real world is a lot stranger than any science fiction I've ever seen.
Understanding it is a major challenge.
So, what do you know about physics?
Just aced a test on it.
So?
It's the study of the nature of the world around us. Motion, forces,
Energy.
The physics of the everyday world is classical physics. So you're looking for a challenge.
sure.
Bring it on.
Follow me.
Where'd everyone go?
This challenge requires your full attention, no distractions. Ever heard of the double slit experiment? Step 1 of the challenge.
Tennis balls are classical objects. Let's see what happens when we fire some at the barrier.
What happened?
Some of the balls went through the slit and left marks on the wall at certain spots.
Right.
The distribution of marks on the wall lines up with a single slit. If we open the slit to the right, a similar distribution builds up.
What if both slits are open?
Good question.
With both slits open, we get the same distribution we'd get if we did the experiment with one slit at a time, then combine the results. But this result doesn't just happen with tennis balls. We could have used apples, shoes, or grains of sand, because all classical particles produce the same overlapping distribution. It's the trademark for how localized particles behave in the double slit experiment.
This is where I come in. You just did. See, dude? Dab your finger in the pool, will ya?
What pool?
The one right over there. Just one small tap. Cool. Nice.
The wave spreads out from its source.
Now it's your turn. Waves, man. Yeah.
With repeated waves, we see the formation of crests and troughs as the waves spread farther.
Now, both of you at the same time.
Whoa.
When two waves overlap, they interfere with each other. When crests meet, they form an even higher crest. When troughs meet, they form an even deeper trough. We call this constructive interference. Places where it happens are called interference maxima. When a crest meets a trough, the two cancel each other out. We call this destructive interference. Places where it happens are called interference minima. The overall pattern alternates between constructive and destructive interference, between interference maxima and minima. This is called an interference pattern. Just as two waves interfere when they cross over each other, one wave produces the same interference pattern when it passes through the two slits.
That interference pattern is a trademark of water waves spreading out and overlapping.
All right, but what about other waves? We're gonna do a double slit experiment with light?
Why not? Thomas Young did the first one with sunlight over 200 years ago.
What did he find?
You tell me.
Cool.
So, light produces an interference pattern too.
Everything we model as a classical wave. Light, water,
Sound.
yep.
All right. I think we've covered the necessary points about classical physics. In a double slit experiment, particles produce a distribution of localized marks.
And waves spread out to produce an interference pattern.
Not enough of a challenge, perhaps?
Perhaps.
I'll take that to mean you're ready for a real challenge.
Sure. Sure.
Yes, we're ready.
Shall we?
Yeah.
Okay. Let's go. Now then, what can you tell me about the subatomic world?
The stuff that's inside of atoms.
Electrons, protons, and neutrons.
Let's start with electrons. Do electrons behave in the same way as classical particles? How might we find out?
A double slit experiment.
With electrons?
Why not?
Will the electrons form the same distribution that the tennis balls did?
Or an interference pattern like the water waves did.
Or?
Or what?
We were driven there by experiments and the desperate struggle to try to understand experimental results.
So we should be able to get the pattern a little bit higher, right? So maybe again the deflection plates?
Herman Battlein and his team at the University of Nebraska-Lincoln are performing the double slit experiment with electrons. It's the latest in a series of similar experiments dating back to the 1960s.
One of our goals was to be as close to the original thought experiments as we could possibly be.
The scale of the experiment is incredibly small. Each slit is only 100 nanometers wide. That's 1,000 times narrower than a strand of hair.
It takes a lot of time to get things lined up, a lot of patience to get things to work properly.
The experiment takes place inside this metal tube with a super hot filament firing electrons at the slits. After passing through the double slit, electrons strike a detector screen, which produces these green dots.
At first glance, you would expect that for classical particles, you would just get the addition of the two distributions. If you actually do it, there's an enormous surprise in store for us.
Instead of the distribution we'd expect from classical particles, electrons produce an interference pattern.
Electrons making an interference pattern. How is that possible?
Maybe the electrons are bumping into each other and repelling.
But how would that create an interference pattern?
What if we fire the electrons at the screen one at a time?
Electrons? One at a time?
Like classical particles?
Yes, like we did with the tennis balls.
Then they should form the same distribution the tennis balls did.
Should they?
If you were thinking of that wave as being built up out of many electrons, then surely the wave is gone, and surely the interference pattern must disappear.
The signal of the electrons hitting the detector screen is transmitted to a computer. The left image shows the electrons striking the screen individually. The right image reveals a pattern that is built up over time. Incredibly, after a large number of electrons hit the detection screen one at a time, they still produce the same interference pattern. So individual electrons behave like particles in arriving at specific spots on the screen. They also seem to behave like waves in building up an interference pattern over time. This shows that electrons have a dual nature. Physicists call this nature the wave-particle duality.
It's always amazing that we can actually see something that is a quantum mechanical effect on a physical screen in our lab. It's very rewarding to be able to actually do that, and it's a lot of fun.
And really excited about the double slit and what we can do in addition to what we've done so far.
You can look at this and you start pondering, what is causing this?
To explain the behavior of electrons, we need the idea of a wave. We need the idea that a wave can pass through two slits at once. So certainly there's something wave-like about electrons. There's also something particle-like.
So the electron is both a wave and a particle.
In some situations, an electron behaves like a particle. In other situations, it behaves like a wave.
Wave and particle behavior together.
You might think of it as a split personality. Like us.
What do you mean?
You're not separate.
In the world of classical physics, we are separate. In the subatomic world, we're two aspects of the same object. Yeah. That's wave. Particle.
Duality.
It takes a while to get used to it. It's not easy at the first sight to understand it, but as you learn more and more, it's just amazing, all these possibilities.
Since it behaves like a wave, an electron has a wavelength. This wavelength is called the de Broglie wavelength. It's related to the electron's momentum by this equation. The symbol h is a universal constant with an incredibly small value. It's called Planck's constant, after German physicist Max Planck, who discovered it in 1900.
Are you enjoying the ride so far?
It's pretty crazy.
Welcome to quantum physics. I should warn you, it's only the beginning. Remember Thomas Young's double slit experiment?
Yeah, it showed that light produces an interference pattern.
Right.
So light is a wave.
Right again. But what happens if we turn down the intensity of the light?
Like we did with the electrons.
Exactly.
At Brown University in Providence, Rhode Island, researchers are performing the double slit experiment with light. They have very sensitive detectors that can detect light even when it's extremely faint. When the intensity of the beam is turned down, we see that light hits the screen as individual, localized particles. This provides strong evidence that light is made of tiny bundles of energy called photons. The energy of a photon is equal to the product of Planck's constant and the photon's frequency. the higher the frequency of a photon, the more energy it has. After many photons hit, the same interference pattern appears on the screen. So like electrons, light exhibits wave-particle duality.
When we study light, it can be a wave, completely a wave. And then we change the experiment and it looks entirely like a particle.
So now we have light and electrons on the wave-particle duality list.
That should do it.
Not quite. Wave-particle duality isn't limited to light and electrons. Wave-particle duality is one of the defining features of all quantum objects.
Like electrons and light, protons, neutrons, and atoms behave like particles in some situations and like waves in others. Some researchers have even observed wave behavior in molecules. In 1999, researchers in Vienna, Austria observed an interference pattern for molecules made of 60 carbon atoms. Since then, they've continued to increase the size of the molecules in their experiments.
The first question is how big, how complex can such a quantum object be before quantum mechanics breaks down?
To me, this is just a technological question. We are now learning to see quantum effects for larger and larger objects, and I'm convinced that someday we will actually see them on an everyday scale.
No one knows where it'll break down or if it will break down at any point, and nobody can delineate a sharp boundary between the classical and the quantum worlds. This is a major open question.
So the electrons hit the screen one at a time like particles.
Right.
But when both slits are open, we get an interference pattern, like waves.
Even when we fire them one at a time.
Correct again.
Doesn't that strike you as a little weird? I mean, how can something that hits like a particle produce an interference pattern?
Does each electron go through both slits, like a water wave does?
All good questions.
I got it. If we want to know what the electrons are doing, why don't we just look at them?
Yeah.
Someone already thought of that.
Researchers in Tübingen in Germany placed measuring devices next to the slits. When they fired electrons at the slits, half of them went through the left slit and half went through the right.
See? Told ya. Problem solved.
Not so fast.
When the researchers looked at the screen, something had changed. The interference pattern was gone, replaced by a completely random distribution.
Measuring a system disturbs it, and so even though there's interference there when you're not looking at it, as soon as you look at which slit the electron has come through, it collapses into one of those two possibilities and looks like it's acting like a particle.
Many other experiments have also shown that measuring a quantum object disturbs it. It's as if the quantum world is resisting our attempts to unlock its mysteries.
In classical physics, when you measure something, that object stays the same. We're constantly being measured, and I don't change just because the light is shining on me right now. But in quantum physics, if you shine light on an object, you disturb it inevitably. So in particular, when we try to measure something in quantum physics, then what we're trying to measure will be gone.
Consider, for example, that you're trying to measure the position of a basketball. If you can use your eyes, the basketball's flying across the room, you can see where it is, and you don't disturb it. But now pretend you were blind, and all you could do was throw, say you had a pile of baseballs there. You're throwing the baseballs at the basketball, some of them will hit, they'll come back, they'll tell you where it was, but every time they hit, they kick it a little bit, and that ruins the information. And in quantum mechanics, you don't have the option of doing anything other than disturbing the system when you measure it.
So, we can't measure electrons or other quantum objects without disturbing them.
That's right.
You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally know.
The recent quantum theory seems so counterintuitive, is that we have been brought up on classical physics.
Physicists have developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
There's something called the collapse interpretation. The idea is that there's only a wave that passes through the slits, and then the wave, when it arrives at the screen, it collapses, so it's only detected in one of the many possible places it can be detected at the screen.
It seems to behave as a wave in between the source and detector, so it can go around these barriers and go both ways through the slits.
The pilot wave interpretation says that electrons are real particles, like tiny, tiny tennis balls, guided by an unseen wave.
In this case, you can explain why the particle is only detected in one place behind the slits, because there's only one particle.
It's this pilot wave that tells the electron what to do. So the pilot wave mysteriously knows about everything, where everything is in the universe, and it feels whether or not there's a one slit or two slits, or one slit open or the other slit open. And it can somehow tell the electron about this and move it around and get it to go different places.
If wave-guided particles aren't your thing, how about parallel universes? The many worlds interpretation explains the double slit experiment by saying that parallel universes are being created all the time.
So in quantum mechanics, we have superposition of different states, and the many-world interpretation says that all these different superposition of states are equally real.
The world literally splits into many copies, and so we only see one thing happening, but there are people in another parallel world who see another thing happening.
While some researchers attempt to construct mental images of the quantum world, others think this world can't be pictured. The Copenhagen interpretation says that we should focus only on the results of measurements in quantum experiments.
When an experimenter enters a lab and interacts with a quantum mechanical system, the Copenhagen interpretation says don't ignore that interaction. It's a crucial piece of what's happening.
It's very powerful to restrict yourself to questions about what we can see. It's very powerful to restrict yourself to questions about what we actually do, because that teaches you to think about the experiment in a very honest way, in a way that appeals directly to the experiment itself without invoking extra theoretical ideas.
In the double slit experiment with electrons or with photons or with buckyballs or anything, the question is what happens between the source, the double slit and the screen. John Archibald Wheeler, famous American physicist, said, "This is just a smoky dragon," meaning that we cannot talk about it. We can mathematically describe it, but it is impossible to make a picture.
I think none of these philosophical discussions bear fruit. The only thing that bears fruit are the calculations.
There's no consensus about which interpretation is right, but they all predict the same results for all experiments.
We really do know what's going on at the subatomic level. We have a complete and accurate mathematical description of what happens.
That mathematical description is something everyone agrees on. It allows us to make incredibly accurate predictions, and that's very useful.
Something that people didn't anticipate is that if you have a weird version of reality, then you can make that weird version of reality do some work for you.
Do some work for you? That's weird.
How can quantum work for us if we don't even know what's going on?
We know what's happening. We just don't know why.
If we can't measure a quantum object without disturbing it, what can we possibly make?
Plenty.
Quantum physics is invading everyday life, even if we're not aware of it. And so as the world becomes increasingly more technology-oriented, we're just going to see a world that is increasingly quantum physics-oriented.
Many technologies take advantage of the wave behavior of electrons. One of them is the electron microscope. An electron with a large momentum has a wavelength much smaller than visible light, so scientists use electron microscopes to resolve objects down to the level of individual atoms. We can look at strands of DNA, examine viruses, and design nanotechnologies. The particle nature of light is at the heart of a range of everyday technologies. Traffic lights, solar panels, barcode scanners, and remote controls are all devices that incorporate quantum effects related to photons.
Inside modern devices for information processing, like CD players, cellular phone, computers, there are, at the brain itself, there's an element called a transistor. And the transistor would not work today if we would not have the laws of quantum mechanics.
We can control the flow of electricity. We can amplify it, we can turn it off, we can turn it on. Our ability to turn things on and off, control the flow, gave us logic gates. Those logic gates, when we were able to replicate them on a mass scale through commercialization of that discovery, led to integrated circuits led to computers, computers led to the information age and the internet.
If you do not think quantum mechanics is important and you do not like quantum mechanics, you can choose to live your life without it. Please get rid of your cell phone, your iPod, your computer, your all electronic equipment, and then you can live your life without quantum mechanics.
I had no idea my phone was quantum.
No one knew the range of technologies possible when the theories were first presented 100 years ago. But our knowledge developed over decades.
Quantum mechanics has revolutionized the way we live our life. The development of the technology and applications enables more science to be done. As more science is done, more technology and more applications are developed.
At the Institute for Quantum Computing in Waterloo, Ontario, researchers are developing a range of new quantum technologies. Quantum cryptography takes advantage of the concept of measurement disturbance. It's the basis of ultra-secure secret codes that are starting to be used by banks and governments to safeguard highly sensitive information.
In quantum physics, when you make a measurement, it doesn't tell you everything about the system you're looking at. And further, just by looking at the system, you change it. In cryptography, we can use this to detect eavesdroppers. So not only can an eavesdropper not get all the information about a system, but will inevitably change the signal and can be detected. So it's quite clever, actually.
Researchers are also using quantum physics to build a new breed of ultra-powerful computers.
So the idea of a quantum computer is, suppose you built a computer out of individual atoms or other very small objects that were behaving quantum mechanically. Then instead of just having one number in its memory and doing computations on that one number to get an answer, it could have, in some sense, many numbers at the same time and do computations on all of them. And so consequently could solve some problems much faster than any regular computer.
In the case of quantum computing and quantum cryptography, we go much deeper in the quantum world, much kind of places where we don't only put our big toe in the ocean of the quantum world, but really go and swim in it.
And what's really exciting is that we can't even imagine the kinds of discoveries that our future physicists are going to make. But what we know is that they're going to absolutely transform society.
Was that enough of a challenge for you?
Yeah, the world works totally differently than I thought it did.
And there's still so much left to figure out.
Lots of challenges.
Lots of opportunities.
Why was the world made in such a funny way? We don't know the answers yet, but that's what makes science exciting.